All right. Yeah. Oh, I do. Yeah. And the video's online too.
Okay.
All right. So I had somebody email me a question. They said, if we're finding the dot product, so let's slide up here and look at some of the dot product problems. Use the dot product to find the magnitude of u. It says, okay, I think up here, find the dot product. If it has i's and j's on it, do you keep the i's and j's? Are those part of what you multiply by? Nope. Okay. They're just, so this 3i plus 4j is another way of writing 3 comma 4. Okay. It's just indicating in terms of the standard unit vectors. And remember, the standard unit vectors give us kind of a coordinate system. They give us kind of a notation that we can rely on and know we're working with the vectors other than thinking, okay, this is like x and this is like y or something like that. Okay. So if you were finding the dot product between the two of those, it is just the 7 times the 3, the 4 times the negative 2, and then you add those together. Okay? Let's take a look at number 23. On number 23, it says find the angle between the vectors. So there are a couple different ways that you could do this. So let's look at this for just a second and see if we can think our way through this. Okay? This right here is the cosine of pi thirds. That is a number that we know. And that's the sine of pi thirds, also a number that we know. So if I were to think about what this is in terms of writing it in terms of numbers and i's and j's, cosine of pi thirds, 1/2. So this is half I plus sine of pi thirds, radical 3 over 2j. Or if I wrote it in component form, it's just 1/2 comma radical 3 over 2. Now, does anybody recognize that? It's a coordinate on the unit circle. So what's the magnitude of this vector? What's the magnitude is 1. So this happens to be a unit vector. Remember when we introduced unit vectors, I said vectors in the standard directions are easy to recognize. That is a unit vector. It's 1 unit in length that happens to be pointed at 60 degrees, at pi thirds. Okay, let's take a look at this one right here. Okay, so if I were to write that in terms of i's and j's and numbers, cosine of 3 pi fourths. Negative radical 2 over 2 I. Sine of 3 pi fourths? Radical 2 over 2 j. If I were to write it in component form, that would be negative radical 2 over 2 comma radical 2 over 2. Now, once it's in component form, okay, even just with these numbers right here, or for that matter, if you had to, even if it was written in terms of the cosine and the sine of each one of those angles, okay, let's see, there was that formula, and I said it would be nice if you had it memorized. The angle between two vectors is the cosine inverse of, what goes on the top? The dot product, u dot v, over product of the magnitudes. So magnitude of u, magnitude of v. Now, because of these particular ones, how long did we say each one of these should be? 1. So what's each one of those magnitudes? 1. Oh, we're going to say in just a second. Let's find the dot product. If I multiply the two of these together, don't I get negative radical 2 over 4? Okay, so I get negative radical 2 over 4. Okay, and if I multiply the two of these together, don't I get radical 6 over 4? So if I do the cosine inverse of that stuff, let's see what we get. Now go ahead and have it in degree mode. 75? Interesting. Is that right? Okay, and stop and think about what's valuable here. I heard a whole bunch of, that's how you do that. That's fabulous. But was any one step here very difficult?
No.
No. In fact, if we were to rewrite this and say, well, you know what? These are the two horizontal components. These are the two vertical components. So I could rewrite that numerator this way. Let me see if I can create enough space to write this. I could do the cosine inverse of, if I did the dot product, it would be these two things multiplied together. So that would be the cosine of pi thirds, cosine of 3 pi fourths, plus sine of pi thirds, sine of 3 pi fourths. So forgive my writing there, but you get the idea, right? And then that's the dot product. And how long are each one of those? Each one of those is 1. Okay? If you did cosine inverse of that stuff right there, use the right amount of parentheses, you'd get 70, well, I guess you'd have to have it in radian mode. You'd get the radian equivalent of 75 degrees, which is probably about 1 point something. Okay? Any questions? Okay. Does the formula work? Yes, it does. Now, I want you to stop and think about something else. Yeah.
Just do 3 pi over 4 minus pi thirds.
Oh my gosh. Yes, we could. Let's stop and think about where these are. This vector is 1 unit in length, right? Pointed what direction? What's the direction angle for this? 60 degrees. Isn't that a point on the unit circle? So wouldn't it be right here pointed at 60 degrees? Okay. Now, it's nice that it's 1 unit in length, okay, especially for these other calculations that we need, but it's actually pointed at 60 degrees, right? This thing right here tells us what the direction angle is. Good? By the way, what number is sitting out in front of each one of those? A 1. So wouldn't you be able to tell that it's 1 unit in length? Because isn't that the formula for the horizontal component, magnitude times the cosine of the angle, magnitude times the sine of the angle? Make sense? How long is each one of these? You can see what it is now. See how all this stuff fits together? Okay, and this one happens to be pointed in the direction of 3 pi fourths, 135 degrees. So if the question is, how far is it in between the two of those? 135 minus 60, or 3 pi fourths minus pi thirds, and you've got your answer in radians or degrees, whichever one you need there. Okay? Pretty clever, isn't it?
Yeah.
Okay? Especially the fact that you can write down the vector in terms of trig functions and an angle. And you can look at it and see the number out front, and you can say, oh, wow, that's got to be 1 unit in length because of the number sitting out in front of those trig functions. Good there? Okay. All right, let's turn our attention back to, we left off right here. Okay? We were talking about projections. And projections sound like they're pretty darn awful. They're actually not that bad to work with. We took this picture right here, and I showed you a picture right there, so we could kind of get some idea of what we were looking at. And when we say the projection of U onto V, and I said the way to look at this is think about V is down below just a little bit. It's written subscript. So we're projecting U onto V. We want the portion of U that goes in exactly the same direction as V. All right? That's called a projection. And we tilted it just a little bit, and we said, look, if U is heading off in this direction and V is heading off in this direction right here, what I'd want to do is I'd want to figure out how much of this one right here translates or could be shifted down here. So this right here would be the projection of U onto V. So I want that little piece right there. So what's important to know is what is the angle between the vectors, because then I can make a little right triangle right there. So I mentioned tilt your head just a little bit, because hopefully in the long run this makes more sense. So tilt your head just a little bit and look at this right triangle right here. I know how long this side is right here. I know that's the magnitude of U. I can figure that out. We know how to find magnitudes really well. Okay? If I want to know how much of this magnitude, how much of this direct length I can put in this direction right here, I make a little right triangle there. And this then would be the adjacent side of that right triangle. And what trig function do I use to find the adjacent side if I have the hypotenuse? I use a cosine. So we said in order to figure out this right here, it's going to be the projection of u, it's going to be this magnitude right here, times the cosine of that angle right there. Because if I did cosine of theta equals, this would be the adjacent side over the hypotenuse. So I'd multiply both sides by the hypotenuse, and what is the hypotenuse here? It's the magnitude of u, right? So it's the magnitude of u times the cosine of the angle between the two vectors. And then we said, how do we make it so that it's the right length and goes in the right direction? Okay, this is the right length. How do we make it go in the right direction? Well, we said find a unit vector for v. And how do you find a unit vector for v? You take v and you divide it by its magnitude. Or multiply by 1 over its magnitude. So I've got a vector that's 10 units in length. How do I make it 1 unit in length? Divide by 10 or multiply it by 1/10. Everybody good there? Okay. Does the idea behind this make sense? Okay. So I want you to write this down. Okay. This is the magnitude of u then it's going to be times cosine angle between times, what was this? What is v over the magnitude of v? Unit vector for v. Okay, that's how you project u onto v. That's how you project u onto v. Okay, and what I said is they came up with this formula right here. I mean, this is the formula we're going to use. This is why it works out that way, but can anybody tell me how to go from here down to here? Because this is the idea, but we don't do it like that. We use this formula right here. Nobody got it? Okay. Look back in your notes and find a formula for the cosine of the angle between the vectors. Okay, so I'm going to write down the magnitude of u. I'm going to replace the cosine of the angle. The cosine of the angle is, tell me what it is. Isn't it u dot v? U dot v over product of the magnitudes. Product of magnitude of u, magnitude of v, and then times v over the magnitude of v. Everybody good there? Okay, now these are all, watch, number, scalar, number, that's a scalar, number, number, number. Where's the only vector here? Vector v. Vector v is the only number. So if these are just numbers, everything except for that guy right there, that's a vector. Everything else is just a number. What can I do with these numbers? Treat them like I would any other numbers in a fraction problem. Any other factors in a fraction problem. I'm going to cancel this one with that one. Can I cancel anything else? No, but I could rewrite the way this is written. This is magnitude of v times magnitude of v. Magnitude of v times magnitude of v. V squared. Okay. So this is where we get the dot product of u and v. The magnitude of v, quantity squared, times vector v. Okay. This stuff right here, these are all numbers. That right there, that's a vector. So the answer to this is going to be a vector. It's the projection of u onto v. It's how much of this length right here do I get to put in the same direction as v. Okay, any questions? Okay. You normally don't see this in books, but this might be a little bit easier. U dot v. Are dot products pretty easy to find? Okay, are magnitudes harder or easier than magnitudes? Sorry, are I said the same word twice, didn't I? Okay. Are magnitudes harder or easier to find than dot products? They're a little harder because you got to square and you got to take the square root and all that sort of stuff, right? Okay. Do you have a formula for the magnitude of v squared? Look back in your notes. It's on the first page. What's that? What about the magnitude of u squared? U dot u. So if I want the magnitude of v squared, couldn't I do v dot v? V dot v would be pretty easy, wouldn't it? Now, the idea is the same. We talked about why that is. Okay? But then it's a dot product with u and v dotted with itself times vector v, and we're all set to go. That would be the projection. This is a very standard formula. That's the one that you're going to see. Again, if I wanted you to use this, I will give you the formula. The thing I like about this is we're really good at finding dot products. Dot products are very easy to do. Okay, and that way you've got, these are just numbers, very easy to find, times it by the vector v, and you're all set to go. Any questions? Okay, sure? Okay, go ahead and take a look at the next example. It says project 3, -5 onto 6, 2. Project 3, -5 onto 6, 2. Now, I'm going to slide this right here. Well, I mean, I know we can see some of the answers. You can see a whole bunch of work down here, but what I want to show you is this. Okay? The projection of u onto v should be the dot product of the two of these. So if I find the dot product of the two of those, that's going to be 18 minus 10. So that's going to be 8. The dot product of v with v. So don't I just square 6? 6 times 6. 2 times 2. 40. And then what do I multiply it by? Vector v. Vector v is 6, 2. So I'm going to call this the fraction 1/5, right? 6, 2. I'm going to multiply through, and I end up with 6/5, 2/5. Any questions? Okay. Same answer. Okay, so our projection's very hard to come up with. Okay, good? Okay, that is this little piece right here. It's not very long. It's a pretty small vector. You'll notice that it's 1 1/5 in the x direction, in the horizontal direction, and only 2/5 in the y direction. So it does head off in this direction, kind of a pretty low angle. We didn't have to figure out what the angle was in between them or anything like that. We figured that stuff out up here. We figured out how those things work up here, and then we used the formula to figure it out for us. It's kind of the equivalent of, let's do all the hard work figuring out what the quadratic formula is, and then from then on, when we have to solve the quadratic, we can just plug the numbers in wherever they go, and we relied on the fact that we constructed it right. Is everybody good there? Okay, there is a bunch of other work on here, because what it says is, find the projection of u onto v, then write u as the sum of two orthogonal vectors. Again, what does the word orthogonal mean? Perpendicular. So it wants it as the sum of these two vectors. So the one that we don't have is we don't have this one that's perpendicular to v. So here's what we do. And this relies on this fact. Remember, if you take a vector, we've always been really good at decomposing this vector into a horizontal part and a vertical part. So tail to tip here, okay? So we're treating this like the resultant, and we're saying, look, if I take this one and add them together, I get that right there, okay? So notice that it says, so here's what we're going to say. U is going to equal W1, the projection of U onto V, plus W2. We want it to be the sum of the two of these. Now, do I know what U is? The original vector U is this vector, 3, -5. Do I know what W is? Sorry, W1. I do. It's that projection right there. So it's 6, 5, 2/5. Do I know what W2 is? I don't, but take a good look at this. These are just numbers, equals these numbers plus whatever these numbers are here. It's like an equation. So how do I solve that equation? Subtract the projection from the original vector, okay? And that's what they're doing right here. This is the work that they're showing right here. If you want to figure out what's left once you've taken off the projection, take the original one and subtract the projection. So they do that work right here, and they end up with 9/5, -27/5. And then what are they showing right here? Okay, again, we're practicing reading a textbook. What are they showing right here? Why would they show this? Somebody tell me what this shows. What does this sentence right here show? It says if you take the two projections, the one that's parallel to V and the one that's perpendicular to V, normal to V, orthogonal to V, and add those together, what do you get? You get back to the original vector. So remember yesterday I talked about partial fraction decomposition. Take the original fraction, break it into the parts that it came from. Okay, we're doing vector decomposition. Okay, only we're decomposing it in a specific way. We're taking that vector U and we're breaking it into one vector that's parallel to V and one vector that's perpendicular to V. And we just come back here and say, hey, you know what? If you add those two together, you do indeed get the original vector. Okay? All right. Does that idea make sense? Okay. Any questions? Okay. Because you probably could get through most of maybe up through 30 or 40 or somewhere like that in the problems. The rest of the problems deal with doing projections. And again, if I put one of the projection problems on the test, I will give you the formula for it. So you would have to know how to use it. Okay? If you are planning on going into some heavy-duty engineering or science or math or something like that, physics, they use vectors all the time. Okay? And all you need to do is get that idea in your head, get it cooking right now, and then you'll be in good shape when you see this again. You probably won't see this again. You'll see it a little bit in 1060, and then you'll see it big time when you get to Calc 2. Okay? Any questions? Okay, so let's take a look at a kind of a familiar problem. And let's read through their work and let's see what they did and see if we can make sense of it. Okay? So it says we've got a 600-pound boat sitting on a ramp inclined at 30 degrees. So this is a little bit steeper ramp than it was before. Okay? What force is required to keep the boat from rolling down the ramp? What force is required to keep the boat from rolling down the ramp? So the force goes straight down. So I'm going to draw it like this so we've got a little bit more room. Okay? That's 30 degrees right here. This weight right here is 600 pounds. It's going straight down. As we talked about before, when we've got a force sitting on an inclined plane or sitting on a ramp, that force is broken into two different components. It's broken into a component that goes straight down the ramp. It wants to slide straight down the ramp. And then it's broken into another component that's perpendicular to the ramp. Does this look familiar at all? Okay, so if we called this the ramp and we called this the weight, this piece right here would be the projection of the weight onto the ramp. And what we want to do is we want to figure out how big is that vector? What is that vector? So what they do here is they say the force due to gravity is negative 600J. Negative 600J. Why negative? Because it's going down, and 600 because it weighs 600 pounds, right? Okay, so another way that we could write that would be in component form, 0, comma, negative 600, okay? Let's look at this. See if you can figure out what that is without reading this sentence right here. What does this represent? Radical 3 over 2, comma 1/2. Doesn't that represent the ramp? Okay. What it really represents, because you'll notice that these are written down as positive, what it represents is a vector that's 1 unit in length that goes in that direction right there. Okay? So, unit vector along the ramp, says it right there. Force due to gravity, unit vector along the ramp. So I'm going to write that one as radical 3 over 2. Again, I like component form. The I's and J's are great, but I kind of like component form. Okay? So this is the weight, and this is the ramp. And what did we say we wanted to do? Project the weight onto the ramp. Project the weight onto the ramp. Project W onto R. So if I were to do that, what goes on the top? Isn't it the dot product? Okay, so it's going to be W dotted with R. It's going to be R dotted with R times R, right? Is that correct? Okay, now I don't want to hear so many, oh my gosh, when we do this. Okay, let's stop and think about this for just a second. When I dot these together, 0, negative 300. Okay, please don't do the math. Please don't do the math. What do I get when I dot R with R if it's 1 unit in length? You get 1, don't you? Isn't that right? It was a unit vector. Is that a huge advantage on this one? Huge advantage. Okay, that's why we like unit vectors. So this is a 1. And then what is the vector R? Radical 3 over 2, comma 1/2. And then what do I do with this right here? Distribute it through. Now, if you'll notice what we've got here, we've got negative 300 and then the vector in component form like this. 1 unit in length, multiplied by negative 300. Is that the same answer as we got here? Exact same, isn't it? Okay, any questions? What's the difference between what we were doing and what they did? What's the difference here? Okay, we called them different things too. We called them the weight and we called them the ramp. Okay, what's the difference between the two of these? Okay, we did the dot. We did R dotted with R, and does it matter? No, because it's going to be the magnitude squared. It's going to be that square root without the square root on it, right? Because once you square it, it's the same thing. Okay, they did theirs in terms of I's and J's. Same answer though, right? Okay, any questions? Okay. What if I said, okay, that represents the force that's rolling down here. Okay, that's how much it wants to roll down there. Okay, that's why it's negative. Okay, it's going to run in a direction this way. Okay, what if I said how much force do the tires put on the ramp? Okay, what's sticking it? How much force is sticking it to the ramp? What would we want to find? Okay, if this is the ramp force, this would be, we could call this the wheel. Oops, we couldn't use a W for wheel. Okay, we use N for normal force, okay, or orthogonal force if we wanted to. How would we find that? Yeah. So we could take, well, we'd do this. We'd take the ramp plus the normal force equals the weight. And if I want to know the normal force, I'd take the weight and subtract the ramp that we just found. Okay? Does that make sense? Okay. I don't think it asks for that, but if it did, that's what you'd do. Okay. Any questions? Okay. Last little bit. And again, these are things that if you've had physics, these come up. You do relatively simple examples when you're in a physics class. Maybe you do some like this, but here's the basic idea. Okay, and I'd like you to write this down. Work equals force times distance. Work equals force times distance. W equals F times D. W equals F times D. So if I had a 60-pound force and I moved something 10 feet, there's the force, there's the distance. How much work have I done? I've done 600, and what would the units be on this? Anybody heard of these? Foot-pounds? Okay, they're called foot-pounds. Okay? So I've done 600 foot-pounds of work. All right? Any questions? Okay, so in this problem right here, you'll notice what we've got in this diagram here is, imagine taking this block and moving it from P all the way to Q. And the smartest way to do this, so everybody here's probably played with a wagon, right? The smartest way to do this would be to get really low and just pull right along here. So we're pulling in a direction parallel to the movement. Okay? Does it work very well, or is it as efficient to pull like this? No, especially the way I've got this drawn, if we thought of this to scale, you're pulling more up than you are pulling this way. Okay? So even though this is a much bigger force, it's not even pulling as much as that first force that I drew right here. Okay? So that's not a very efficient way to do that, but that has to happen sometimes. If you're an adult and you're pulling somebody in a wagon, you don't really want to bend down like this. Okay? That's actually harder on the legs and stuff like that. Okay? But if we can apply it in a direction that's parallel to it, it makes it very easy. But most of the time we end up with something like this. We end up with a force that's offset from the direction of the motion. But pulling up doesn't help at all. And we also don't lift it up, or we'll assume that we don't lift it up. So if we haven't moved it up at all, we haven't done any work in the upward direction. All the work is going to be done by moving it from here to here. So take a good look at this right here, and look at the notation that they've used here. How do we figure out the force going in this direction? What does that say? It's the projection of F, that force, in the direction of PQ. Okay? So the way we do a problem like this is we need to figure out a projection. So I'm going to slide this down right here. And this gives a couple of different forms. It says the definition of work. Okay? So the projection of F, the magnitude of that force directed in that direction, okay, times, this is a magnitude also. So you'll notice that this is a number and that's a number. So I can find the magnitude of that projection and multiply it by the magnitude of that distance right there, how far it is from P to Q. Or I can take the magnitude of F and I can dot it with the vector PQ. Both of those are useful. They end up doing the same thing. Okay? So on this example right here, it says closing a sliding door. So anybody ever worked on a farm or anything, seen a door like this? Very good. Hop has. Hope, very nice. I'm proud. I'm from Idaho. I see this all the time. So a lot of times they'll have the closing mechanism. It will be at the top or the bottom. It's at the top. Maybe a rope hangs down. Okay. A handle would be very efficient, and those are used sometimes. But let's say you've got a rope right there, and when you're pulling on it, okay, the angle between the track that this door is going to slide on and the rope that you're pulling on is 60 degrees right there. And you're pulling on that rope with a certain force. Okay. And you're going to slide that door over this direction right here. Okay, we want to figure out how much work has been done. Okay? So let's see. Somebody pulls with a constant force of 50 pounds. So they're pulling on the rope at 50 pounds at an angle of 60 degrees. Okay? Find the work done in moving the door 12 feet to its closed position. So using a projection, you can calculate as follows. The projection of F on to PQ. So this is a 50-pound force, 60 degrees. So think about that. If this, so let me draw a picture. This is a 50-pound force, and this is a 60-degree angle. How much of this force projects over to right there? In other words, how long is that right there? How would I figure that out? Hypotenuse, adjacent side. Wouldn't the cosine of 60 degrees equal the adjacent over the hypotenuse of 50? So isn't the force 50 times the cosine of 60 degrees? So there's the 60 degrees. There's the magnitude of the force. Cosine of 60 is 1/2. Magnitude of the force is 50. And what is the magnitude? How far are we going to move that? How far is it from P to Q? 12 feet. So the magnitude of this is 25 in that direction. We're going to move it 12 feet, and when we multiply those together, we get 300. And remember, this was in pounds, this was in feet, so we end up with foot-pounds. Good there? Okay. Read that sentence at the end. Should get the same answer if we do what? Find their dot products. Okay? So let's take a look here. I want you to write these vectors. Okay, so this is the track, and this is the force we're pulling with. I want you to write those two vectors in component form so we can figure out what their dot product is. And let's just make sure it's the same. And the nice thing about this is set up in a very convenient way, which we can do a lot of times. This track happens to be, and even if it weren't, it happens to be running horizontally. So is it easy to come up with the vector form of the track? What would it be? 12,0, right? Let's think about the vector form of the force. The vector form of the force. I'm going to write 50, and then I'm going to write something else. Okay. Cosine of, should I write 60? Technically speaking, if the reference angle is 60 and I went around in standard position, usually we use an angle from 0 to 360. What I should write here is 300, 50 sine 300, right? Is that good? Then the work should be So this should be pretty cool. Check out the dot product. Dot the two of these. I get 12 times 50 times the cosine of 300 plus, what's the other part? 0. Okay, now go ahead and type that into your calculator. Just think for just a second. Cosine of 300? Isn't it positive 1/2? 1/2 times 50 times 12 is going to be 300. Same answer. Good? They both work, don't they? Okay, now, here's why I kind of like that dot product idea just a little bit better. When I found the dot product of the horizontal components, okay, the ones that were going in that same horizontal direction, I ended up with this right here. And that's where all the work was done. When I did 0 times the force, because there is a force, I mean, if he's pulling down, he is pulling in that direction. Can somebody tell me why this is a 0 in the terms of work? Why is that part of it 0? I know he times it by 0. That's numerically the reason it is. Why is it 0 in terms of work? What has to happen in order for work to occur? What is it, Tammy? Okay, you have to have a force times a distance, right? Did we move the door in that direction? Did we move it down? Part of the force was pulling down, but assuming everything's attached properly and everything, no matter how hard that person pulls down, it's not going to go down. So if you don't move anything, is any work done? Nope. And the work only occurs in the direction of the motion. Okay? So hopefully, I know, I've seen several things like this, but imagine he stood right next to it and pulled down really, really, really hard. Would the door move? What if we moved over just a little bit and pulled really, really hard? It would move a little bit, right? Until it was right over the top of him. Okay? And when it's right over the top of him, he's not applying any force in the direction that he wants it to move, so it's not going to move. Okay? You could hang all day on the rope right here and it wouldn't go anywhere. Okay? You pull just a little bit in that direction and it will move until it's right over the top of you. Okay? So the reason this is a 0 is because we didn't move in that vertical direction. No work was done in the vertical direction because it didn't move in the vertical direction. Does that make sense? Okay, any questions? Okay, we've got a couple minutes left. Oops. Okay. Find the angle between the vectors, or let's see, find u and v where that's the angle between the vectors. Determine whether u and v are orthogonal, parallel, or neither. That should be pretty easy, right? Okay. Let's see. Find the projection of u onto v. Do you feel pretty confident about that now? I mean, if you were just asked to do that from scratch, that's a horrible nightmare to figure out, but hopefully you've got that down. Okay. Let's see. I don't think I asked any in this section here, did I? 43? Okay, let's take a look at number 43. It says, find two vectors in the opposite directions that are orthogonal to the vector u. The answers are not unique. Find two vectors in opposite directions that are orthogonal to the vector u. Orthogonal. Okay. So, what's orthogonal again? Okay. This one heads off at 1, 2, 3, 1, 2, 3, 4, 5. So I want to come up with a couple of vectors that are orthogonal. It means they meet at 90 degrees. If they meet at 90 degrees, their dot product would have to be 0. So you could make up some things where the dot product equals 0. So I could do something like this. let's say I've got vector A, so it's A1 and A2. If I dot it with 3, 5, what do I want it to turn out to be? 0. Now, I could cheat and make both of those zeros, right? Okay. What if I made this one, let's see, what number would work well? Let's make this number 5. It says there are no unique answers. There are a whole bunch of different answers. If I find the dot product here, that would be 15 plus 5a2 has to equal 0. Move that over. What does a2 have to be? a2 would have to be -3. Is there one answer? Sure. Now I did that. Did you see why I picked the 5? Okay. Because it would be easy to match that up. Now here's what's interesting. And see if you can figure this out and think about this a different way. Draw this vector on here, or just visualize where it would be. It's right there, isn't it? 5, -3. This one was 3, 5. Do you notice what we did there? Think about the slopes of the lines. What's the slope of this line? Rise over run, right? 5 over 3. What's the slope of this line? -3 over 5. Okay, it's the opposite reciprocal. So let's do one over here. All I need is the slope to be -3/5. So how about I do -6 over 10? Would that work? So what vector does that represent? Which one of these is horizontal? 10 is, and the vertical is 6. And if I want it to go back and up, which of these has to be negative? The 10 needs to be negative. So -10, 6. So see how you can use slope to figure those orthogonal ones out as well? Okay. See what you can do on the assignments. There are several projection problems. I think there's maybe 3 or 4. See if you can figure those out using the techniques that the book showed and how I also showed how to think about them. And then we'll go from there tomorrow. We are going to start 6.5 tomorrow, though, okay?